So actually, I'm viewing the person. She's actually just you guys take attendance at all? We don't take attendance. No, actually, no. About the YouTube, actually live streaming on YouTube. I can. Would you like to see it? I'm not too no, unfortunately, I didn't think so. Yeah. All right, thank you. Yes, you don't need to do the okay, take care.
All right, good morning, William. Can you hear me okay?
Yeah, I can hear you. It turns out you're on the computer speaker though. 1 second. Okay, that should be it. Go ahead.
All right, can you guys all hear me okay?
Yeah.
Perfect. All right, let's get rolling. Good morning, everybody. I hope you are all doing well. We have successfully made it through our second chapter quiz. So as a reminder, there are 5 chapter quizzes in this class, 1 for each chapter, and there is an optional final, which would replace one of whichever your lowest quiz grade would be. We'll talk more about the optional final later in the semester. But now we are sort of going through chapter 3, where we are learning how to figure out the formulas for different types of derivatives so that we don't have to approximate as we were doing in chapter 2. So we're sort of making our methods better and a little more advanced, using what we know to build what we don't know. Okay, so last time we looked at the power rule, which applied to polynomials and power functions. And then we looked at sine and cosine at the end of class. And today we're going to bring in exponential and logarithmic functions. So I'm going to switch over to the doc cam. Okay, so just like with polynomials and power functions, the way that we get our formulas is by really evaluating the derivative using the methods we did in chapter 2. So we're not going to do them out. But the idea is that if we wanted to figure out a derivative formula for 3 to the x, and we wanted to start by approximating at a point, right, to get f prime of 0 or f prime of 1 or f prime of 2, we would be doing that average rate of change process for each and every one of those points. And if we were to plot all of those points on the same graph as the function, we would get something that looks like this, okay? So this is the derivative of 3 to the x, and this black one is the 3 to the x. So what we notice is that at 0, okay, the derivative and the value are really, really close to one another. As a matter of fact, the whole derivative function, which is in red, is very, very close to the function 3 to the x. We can tell that the derivative is also going to be exponential, but we can also tell that it's not exactly 3 to the x. There's a teeny tiny little gap, right? So if we were to then look at 2 to the x, so we have 2 to the x in black. Now I'm going to trace the derivative in red. We get something similar where we see, okay, it looks exponential. It's not quite 2 to the x, but it's pretty close to 2 to the x, right? And so what we're trying to do is figure out what is this derivative function in relation to the one that we are plotting the points for. And so mathematicians, they look for patterns. And what happens is, if you keep plotting a whole lot of these exponential functions, you eventually find the patterns that lead to the formulas, right? So what are these formulas? The first one we're going to look at is a to the x. So this is the generic exponential formula. That's a little small, so I'm just going to write that a little bit bigger. A to the x. Okay. So the first thing we want to talk about is this is an exponential function, right? So an exponential function is a function where the variable is in the power. One of the most important parts of taking derivatives is recognizing what type of function you have so you can apply the correct rule. People don't tend to have trouble applying the rules, but sometimes they mistake the type of function they have and they apply the wrong rule. So we want to make sure we understand that we're looking at an exponential function. And again, that has a number in the base and a variable in the power. It turns out if you look at a lot of these and you figure out the pattern, that the derivative of an exponential function is going to be the same exact function back. So whatever the base was, we just copy down the original function times the natural log of the base. So whatever that number is, we take the natural log of that number. So that means that this term, ln(a), is a constant, right? Because the natural log of 5 or the natural log of 10, those are all numbers, okay? So a quick example of this, we have f of x equals, 5 to the x. Then our rule says that the derivative will be the same thing back, 5 to the x, times the natural log of the base. And the base here was 5. So what I want to do is that we are not changing the power at all. Last class, we had power functions and polynomials, and we were subtracting 1 from the power. We don't change the power at all when we have exponentials. The power stays exactly the same. X stays X. We don't subtract 1. So again, it's a different formula completely when we're talking about exponential functions. So there's 2 special cases of exponential functions that are related that spin off from this property. So the first one is if you have e to the x. So e to the x is an exponential function. E is approximately 2.71. If we apply our formula for the derivative here, it says we're going to get the same thing back times the natural log of the base. Well, we know that e and natural log have a special relationship, and the natural log of e is 1. It's one of the only values that when you take the natural log of it, you get an integer value and not an irrational number. And so here, anything times 1 is just itself. So that gives me the formula that if your function is e to the x, the derivative of e to the x is e to the x, right? And that's because this natural log term happens to be 1, okay? So the derivative of e to the x is e to the x. Now, if we happen to have some number up in the power, e to the 5x, e to the 10x, something like that, we can algebraically rewrite this as e to the c to the x. So we can separate that power this way because when powers are raised to powers, you multiply them together. So you can also separate them that way. So this is now an exponential function where the base is e to the c and the power is x. So when we apply the rule here, right, we get the same thing back. So we get e to the c to the x times the natural log of the base, where the base is e to the c. Now, natural log rules say that if you take the natural log of something raised to a power, that power can come in front. So we have c times the natural log of e. Well, just like last time, the natural log of e is just 1, right? So that means that my final derivative here, let's write it down here, is going to be, we can change this back into e to the cx times c. right? Because again, this last term is 1. So if we have e to the cx, where c is any number, the derivative is e to the cx, so the same exact thing, times whatever that number is. So let's do a quick example of that, and then we'll do a whole bunch of practice problems here. So let's come up here, remove some space. So if you have e to the, let's say 10x, and you want to take the derivative, I notice that it's not just e to the x, and that there's a 10 there. So I get the same thing back, e to the 10x, times the number that's up in the power, so times 10. So we did this algebraically. We will also see how to do this with another method later on in this course, but for now, that's how we're going to think about why this is true, because it is true if you use all the algebra to show it's true. Okay, so let's do some practice problems. For the first practice problem, I just want you to get comfortable identifying exponential functions and then applying this rule to write out their derivatives. So I want you to take 2 minutes and find the derivative for parts A through D for each of these functions, just carefully writing out what the derivative of each one is, and then we'll go through it together. All right, take about 30 more seconds. All right, so let's go ahead and apply our new exponential rule to each of these exponential functions. So for my first function here, I have 7 to the x. So my base here is 7. So the derivative is going to be the same thing back, 7 to the x, times the natural log of the base, times ln 7. Again, ln 7 is a constant, and the function here is 7 to the x. That's the part with the variable. For part B, I have e to the x. That's one of my special cases. So the derivative of e to the x was e to the x. For part C, I have 1.2 to the x. So again, I'm going to get the same thing back, 1.2 to the x, times the natural log of the base. So times the natural log of 1.2. Finally, this one looks a little goofy. I have pi to the x. So again, pi is just a number. So pi to the x is an exponential function. So I get the same thing back, pi to the x, times the natural log of the base. So I have the natural log of pi. Now again, the natural log of pi is just a number. We leave it as the natural log and we don't turn these into decimals unless there's some instruction to do so. So that's just getting comfortable applying this rule here. We're going to now add one more rule to our list, and then we'll do a quick review of what we know. So the other function that pairs with exponential functions is the natural log. And so if we want to do the same type of pattern finding, we could find the derivative by approximating with smaller and smaller intervals at 0, 1, 2, 3, 4, 5, and then look at what type of function that derivative forms. And it turns out that if you have the function ln x, that the derivative ends up being 1 over x, right? So 1 over x is just a function that, as x gets bigger and bigger, gets closer and closer to 0, but that's what the derivative is for ln of x. So we add that to our list. So now we have a list of a whole bunch of derivatives. We have the derivative of a constant is 0. The derivative of a linear term is the slope. We have our power rule. So if you have x raised to some number, then the derivative is px to the p minus 1. We had the derivative of sine is cosine. The derivative of cosine is negative sine. Now we've added in exponentials. So a to the x, the derivative is a to the x ln a. E to the x, the derivative is e to the x. And ln x, we have 1 over x. So these form what are called the basic derivatives. Okay, and I want to be really clear. Sometimes the word basic means easy, but here the word basic means foundational. Okay, so when we start looking at harder and harder functions, we'll talk about breaking things down into the basic derivatives, and that means the foundational derivatives. It doesn't mean that they're easy, because we can see that there's a lot of work and careful, analysis that needs to be done. But when we refer to the basic derivatives, these are the ones that we are talking about. Okay, so now here's our list. And last time we talked about things like the constant multiple rule, the sum and difference rule, and how to find second derivatives when we had polynomials and power functions. And that's going to be the same for exponentials and logarithms. So the constant multiple rule says if you multiply a constant in front of your function, that constant also has to multiply your derivative. The sum and difference rule says if you have terms separated by addition and subtraction, you can just take the derivative term by term. Second derivatives means that you're going to apply the same rules to the first derivative to get to the second derivative, right? So you're just doing the derivative process twice. And so we can use all of these things also with exponential and logarithmic functions. So let's do a problem that will let us practice that a little bit. Okay. So here we have 4 functions, A, B, C, and D, where we have exponential and logarithmic terms. Now that you'll see there's some constants in there, like the 2, the 3, the 5, we have to use that constant multiple rule. And you can see that we're separated by addition and subtraction. So we can go term by term. So I want you to take 2 minutes and see if you can sketch out the derivative of each of these functions by applying the constant multiple rule and using what we know about addition and subtraction. Okay, so take 2-3 minutes and then we'll go through it together. All right, take about 30 more seconds. All right, so let's take a look at these. So we'll start with the first one. Here we're going to go term by term and apply the correct rules. So we start with 5 to the x, that's exponential. So we get the same thing back times the natural log of the base. Then we have minus ln x. So the derivative of ln x is 1 over x. And then finally, we have plus 2 times 3 to the x. This 2 is a constant that multiplies our function. So we have 2 times the derivative of 3 to the x, which will be 3 to the x times the natural log of 3. Now this last term's a little goofy because 2 is a constant and ln 3 is a constant, and usually we combine constants, but we really don't want to do that here because ln 3 is an irrational number, and so we don't have a good way to combine these without turning this into a decimal, which would turn it into an approximation. So we just leave it like this, okay? For part B, again, we're going to go term by term. The first term is e to the x. The derivative of e to the x is e to the x minus, now we have a 3 times the function. So we're using the constant multiple rule. So we have 3 times 1 over x. You can leave it like that, and some people prefer to write it like this. So instead of 3 times 1 over x, we have 3 over x. These mean the same thing, okay? Either way is totally fine. For part C, we start with 10 to the x. So again, exponential, we have 10 to the x times ln 10 plus, now we have a 5 times ln x. So again, we're going to use the constant multiple rule. So we have 5 times the derivative of ln x, which is 1 over x. And then finally, for part D, we start with the derivative of e to the x, which is e to the x. The derivative of 6 to the x is 6 to the x ln 6 minus the derivative of ln x is 1 over x, okay? The more we practice writing out the derivatives for these types of functions, the easier it'll be as things get harder, right? So knowing these types of derivatives really well is really helpful once our functions start to get more complicated. So I just want to remind you, this is really important, that this derivative function is there to tell us the rate of change at any point. So if we were to plug in x equals 1, that would be a number, and that would tell us how quickly the function is changing at 1. What function? The original function. How quickly is this function changing at 1? We'd plug in a 1 here. The reason we're trying to get the derivative functions is so that we can plug in any values that we want, and later so we can think about things like increasing, decreasing, concave up, concave down, all those sorts of things. So we always have to remember all the derivative stuff we're doing. The derivative gives you the slope of the tangent line, which tells you how much a function is changing at a point. So that's always happening in the background. To that end, we're going to go ahead and practice both second derivatives, but also plugging in values, right? We want to be confident in how we plug things in. So there's 2 things happening here. First, we're going to be finding the derivatives plus a value at 1. So the function that you're looking at is 2 to the x plus e to the x minus x to the 2/3 minus ln x plus 6. So there's some terms in here you have to remember how to do the derivative from last time. When you plug in a 1 into the first or second derivative, we are still looking for what's called an exact answer, which means you should only simplify things if it does not change from an exact answer to an irrational number. What does that mean? If you have e to the 1, you're going to leave it as e to the 1, because if you change it to a decimal, it becomes an approximation and it's no longer exact. However, if you have something like 1 plus 4, you can simplify that to 5 because that doesn't change the value, right? It's still exact. So we're going to do a little practice on exactness and derivatives all in this problem. So I'm going to give you about 3.5 minutes. Again, find the first derivative, then plug in 1, then the second derivative, and plug in 1. Okay, try that out, and then we'll go through it together in about 3 to 4 minutes. All right, take about 30 more seconds. All right, so let's go through this. So here again, we see things separated by addition and subtraction. So we're going to go term by term. We start with 2 to the x, and the derivative of that is 2 to the x, ln 2, because again, 2 is the base. Our next term, we have e to the x. So the derivative of e to the x is e to the x. And then hopefully you saw that I snuck in this polynomial or this power term, right? So this is not an exponential. This is one from the class before. So here the power is going to come down, and then we're going to subtract 1 from the power. So we have 2/3 x to the negative 1/3. So that's what I was trying to say when I was saying it's really important that you recognize what type of term you have so you know what formula to apply. The derivative of ln x is 1 over x, and the derivative of 6 will just be 0 because 6 is a constant that's all by itself. So my first derivative looks like this, and if I want to plug in a 1, I'm going to start by just simply writing in a 1 everywhere I see an x, and then I'll figure out what I want to simplify and what I do not want to simplify. Right, so I have 1 to the negative 1/3 minus 1 over 1. Okay, so thinking about this term by term, the first term I have 2 to the 1 times the natural log of 2. The natural log of 2 is an irrational number, so I want to leave that as the natural log of 2. 2 to the 1, however, is just 2. So I can write this first term as 2 ln 2. That's an exact answer. Plus e to the 1. Again, that's irrational. So I can either write it as e to the 1, or I can just write it as e, because anything to the 1 power is just itself. Now, these terms are really interesting. So 1 to the negative 1/3. 1 to any power is just going to give you 1. So here I have 1 times minus 2/3. So this is negative 2/3 minus, and then 1 over 1 is 1. So I don't want to turn the first term into a decimal, but I can certainly combine these two numbers as fractions. So negative 2/3 minus 1 is going to give me minus 5/3. So if this were on a mini quiz or something like that, this is likely what the answer would look like, right? Because I've simplified the things that I can, and I've left anything that would make it an approximation in its whole form. Okay. So now we need to do the second derivative, and the second derivative is sort of deceivingly difficult. So the first derivative, if you remember all the rules, you can go term by term without too much rewriting in algebra, but the second derivative is a little more tricky. So again, in order to get to the second derivative, I go back to the first derivative, and now I look at the first term. So I have 2 to the x times the natural log of 2. Okay, I want to talk about this natural log of 2 for a second. The natural log of 2 is a constant, and so that makes it a constant multiple. So I have a constant times 2 to the x. So I know that the derivative is my constant times the derivative of 2 to the x. Well, the derivative of 2 to the x is 2 to the x times the natural log of the base. So I actually end up with 2 natural log of 2's, one from the constant multiple and one from taking the derivative of 2 to the x. Okay, it's a little weird. Now, the derivative of e to the x is just e to the x, doesn't change. And then here I have to do another power rule. So here I have a negative 1/3 that's going to come down and multiply this minus 2/3. The negatives are going to cancel, and I get plus 2/9 x, and then I have to subtract 1 from the power, so to the minus 4/3. Okay, so be careful with your fractions here. Now, I started with ln x, and the first derivative gave me 1 over x. That was a special rule. I want you to remember from last time that we can rewrite 1 over x as x to the negative 1. Okay, so we get that out of the denominator by taking that 1 that we don't usually write and making it negative. So when I take the derivative, I'm now using my power rule. So the negative 1 will come down and cancel the minus. So I get plus x to the negative 2. Okay, so that's tricky because I went from natural log to 1 over x and 1 over x to x to the negative 2. Okay. So then again, I want to plug in a 1 wherever I see an x. So I just go through and I plug in a 1 everywhere, and then I'll see what I can combine. Okay, so I'm going to go term by term and think about how I would simplify this. So again, the natural log of 2's are irrational, so I don't want to change them. 2 to the 1 I can write as 2. Now, since I have 2 natural log of 2's, I'm probably going to write this as the natural log of 2 squared. There's 2 of them, so if we multiply them together, we get something squared. Plus, now e to the 1, right? Again, I'm not going to change that because if I turn it into a decimal, it won't be exact anymore. Now, what about these terms over here? So again, 1 to any power is going to be 1. So this is 2/9 plus 1, right? So this is 1. So I can combine these two, and again, I'm going to combine them as a fraction so that I don't turn it into a decimal. So 2/9 plus 1 is going to give me 11/9. So this is what my solution will look like. A little bit tricky, so make sure that you feel pretty good about all these steps. If you're sort of struggling with some of the algebra, definitely stop by Drop-In Help to get feedback on doing that, okay? So the next application, which hopefully I emphasized its importance last time, we're going to do 2 practice problems on this, is we're going to look for the equation of the tangent line, where now our functions involve exponentials and logarithms, right? So there's 2 different ones here that I'm going to have you try. And just as a reminder, in order to find the equation of the tangent line, we need a slope and a point. The slope comes from the derivative, and the point, we have half the point given the problem. We need to plug it in to get the y value. Once we have the slope and the point, we use y equals mx plus b, because the tangent line, to find that equation, okay? So same process as last class, but with a new function here to work with, okay? So I'm gonna give you about 3 or 4 minutes, since there's 2 of them to try, see if you can work out the equation of the tangent line, and then we'll go through it together. All right, take about 30 more seconds. All right, so let's go through this process. So again, we need a point and a slope. It doesn't matter which one you do first. So to find our point, we need to plug the x value into the function, because again, this is the point that is shared by the tangent line and the function. It's where the tangent line touches. So if we plug in a 0, we have 2 times e to the 0. As a reminder, e to the 0 is going to be 1. So that makes this 1 times 2, which is 2. So when x equals 0, y equals 2. So our point here, the point where this tangent line touches, is the point 0, 2. The other piece we need is the slope. So we find the first derivative here. So 2 times e to the x, 2 is our constant multiple. So the derivative is 2 times e to the x, because the derivative of e to the x is e to the x. Now that's our derivative in general, but I want to know the value when x equals 0, because that's the slope of the line that touches at 0. So again, I have 2 times e to the 0, which is 2. The slope of my line is 2. So far I have y equals 2x plus b, right? So 2 is from this slope, but I still need to solve for b. So this is where I use my point. I plug in a 0 for x and a 2 for y. So I have 2 equals 2 times 0 plus b. This goes away. And so that tells me that b equals 2. So the final equation of my tangent line is y equals 2x plus 2. So that is the equation of the tangent line to the function 2e to the x that touches at x equals 0. Okay. So let's do this again for the next one. So again, I need a point and a slope. So I can start by plugging my x value into the original function. Okay. So if I plug in a 1, I have 3 times the natural log of 1. The natural log of 1 is 0. Okay, that's sort of one of the other special cases of natural log. So 0 times 3 is still just 0. So now my point here is 1, 0. Okay, when x equals 1, y equals 0. Now I find the slope of my tangent line by going through the derivative. So I take the derivative of 3 ln x. The 3 is a constant multiple, so I'm going to multiply that by the derivative of ln x, which is 1 over x. Again, I need to plug in the value of x that I'm interested in considering, which is 1. So I have 3 times 1 over 1, which gives me a value of 3, which again is the slope of my tangent line. So I have y equals 3x plus b. So here, to solve for b, I'm going to plug in my point. So I have 0 equals 3 times 1 plus b. I need to subtract the 3 over, and I get b equals -3. So the final equation of my line is y equals 3x minus 3. Okay, so again, the slope of this line is the rate of change at that point. So this particular function at x equals 1 is changing by 3 units for every 1 unit we move. So the slope is the rate of change, right? We're just pairing it up to get the entire equation of the line. So like I said, the tangent line is a common sort of example that we focus on through a lot of the derivative stuff. The process is always the same, but what changes is the type of function we look at. Okay, so let's do an application here. This application is really interesting. So in Math 128, if you go on to take that, you'll do a whole unit or 2 on financial math. So you'll be looking at different types of investments and things that have to do with money. So we sort of briefly touch upon this in this class through some examples. So this is sort of the first time we're bringing in the money sort of officially. So I wanted to make sure that we know how to work with the functions themselves before we talk about the derivatives. So this is broken down into several parts to help us sort of understand what's going on. So we're going to talk about it before we do it, just so we're all on the same page. So when you invest money, it gains value depending on a lot of different factors, right? Like the interest rate, how much you start with, all that sort of stuff. One of the factors is how the money is compounded. Okay, so this word compounded, it means how often the interest is added to the principal amount. So the interest is the money you make from your investment. How often is that interest put back into the account to become part of the principal? That's what compounding has to do with. So if interest is added 1 time per year, so once a year your bank looks at your balance and says, okay, apply your interest rate and they drop that money in. That's called annual compounding. So annual means once a year, okay? The equation for annual compounding looks like this, okay? It says FV equals PV times 1 plus R to the T, okay? There's a couple different ways you may have seen this written in other ways, but this is how our textbook does it. So FV is called future value. So that's how much money you're going to have at the end of your investment, okay? PV is present value. So that's the amount you deposit to start your account with. R is the interest rate. We always have to enter that in decimal form. The interest rate is usually given in percentage form, so we have to convert it to a decimal in order to be able to calculate anything. And then time, T, is always going to be in years. So T here is my independent variable, okay? So for parts A and B, and we'll talk about part B in a second, we're just doing some basic calculations. We're not talking about derivatives yet. We're just getting comfortable with these equations. So for part A, we're saying, suppose that you have $1,000, so that's a present value, and that you're going to get an interest rate of 2.5%. I want to know how much money will you have in 5 years. So this is just practicing plugging things in correctly into the right variables, okay? We're going to pair this with part B. So again, this was annual compounding. The more typical way that you will see compounding on, say, a savings account or a checking account is something called monthly compounding. So that means every single month you are getting interest on your money. However, you don't receive the entire interest rate. So if your interest rate is 2.5%, that doesn't mean you get 2.5% every month. What that means is you get 1/12 of the interest rate every month, so that it adds up to 2.5%, okay? So the equation changes that we're going to divide the rate by 12 for each time we compound. But then in the power, we have 12 times T because we're compounding 12 times a year times however many years, okay? So for part B, we're going to assume the same setup as part A. So $1,000, interest rate of 2.5% for 5 years, but now we're compounding monthly. And so the question for part B is, do you expect this to be bigger than part A, smaller, the same? So what I want you to do is I want you to compute the future value for annual compounding for part A. Then I want you to guess whether you think monthly compounding will give you more money, less money, or the same. And then go ahead and compute it using this monthly compounding equation. Okay, so again, this is just plugging things in and getting comfortable with the equations. And then once we have that down, we'll move on to things like derivatives. Okay, so take 2 minutes to try to plug these into the right place, and then we'll go through it together. right, take about 30 more seconds. All right. So again, this is really just about making sure we can plug things in correctly. So the present value is 1,000, that goes in front. We had to convert our percentage into a decimal, so 0.025, and that's raised to the 5th power. Then we have to be really careful plugging everything into our calculator. We're going to want to do the term to the 5th power first and then multiply by 1,000. And when we do, we're going to get $1,131.41. So I rounded to 2 decimal places because we're talking about money. How much money will we have? So at the end of 5 years, you can see we've made about $131 in interest. Okay. When we do a similar thing, but with monthly compounding, again, we have this divide by 12 here, but then up in the power, we have 12 times 5, which is 60. When we carefully plug that into the calculator, we're going to get $1,168.93. So there is a difference between annual compounding and monthly compounding. And we can see that monthly compounding is better for us in terms of how much money we make. So why is that true? That's true because at the end of the first month, when that little bit of interest is put into your account, right, even though it's only 1/12 of this percentage, the next month you make interest on the interest from the previous month, right? And then in the third month, you make interest from the deposits from month 1 and 2. So that adds up. It may not seem like a huge difference, right? But think about if you had $10,000 or $100,000 in this type of account, right? So the more often you compound, the better it's going to be for you, the more money you're going to make. So if you have a choice between banks and one is offering, 2.5% compounded annually and one is offering 2.5% compounded monthly, monthly is the better choice. Okay. So the more often you compound, the more money you make. Okay. So hopefully that makes sense in terms of these equations, what we're talking about. Now, hopefully you notice that these equations are set up, they are exponential functions because the variable is up in the power, okay? And so I'm just gonna go ahead and rewrite as monthly, and then I'm gonna write annually next to it because we don't have enough space. The future value is present value 1 plus r to the t. Okay, so these are our 2 equations here, just so we can get everything on at once. So for part C, we want to take these formulas and find a function that represents the rate at which the future value is changing. So whenever we see the word rate, we should be thinking derivative. So we are trying to find the derivative of each of these functions, okay? So again, these are exponential. This one is easier, okay? Because here your base is 1 plus r. So you just have to think about how that applies to what we've been doing. The monthly one is a little more tricky because we have to make sure that when we have our exponential function, we have something raised to the t. And right now it's raised to the 12t. So we have to change it in order to have one thing raised to the t. So we're going to do a similar trick to what we did at the beginning where we had e to the cx as our special case. How did we get that to just be raised to the x? Think about how we rewrote that. And then we should be able to find the derivative. Okay, so for part C, we're finding the derivative of each of these functions. And then for part D, we are calculating the actual rate at which the function's changing at t equals 5, PV equals 1,000, R equals 0.025. So we're plugging those values into the derivative to get the rate of change for part D. Okay, so take about 3 or 4 minutes, see if you can carefully write out those derivatives and then plug in these values. You should hopefully expect at this point that when you plug these values into the monthly derivative, your rate of change is growing faster than your annual rate of change, right? Because we know that this is more, so we're expecting it to be growing faster. Okay, so take about 4 minutes and then we'll go through it together. All right, take about 30 more seconds. So I separated this into 1 and 2, so 1 for annual and 2 for monthly. So if we want to find the derivative for our annual function, the PV is a constant multiple. So that's a constant that's going to carry with us into the derivative. And then our exponential function is 1 plus r to the t. So according to our rules, we're going to get the same thing back, 1 plus r to the t, times the natural log of the base. Well, the base is the whole entire 1 plus r, because that whole thing is raised to the t. So our derivative looks like that. So PV times 1 plus r to the t times the natural log of 1 plus r. For our monthly compounding, we can't apply our rules the way it's written because of this pesky 12 that's up in the power. So we need to rewrite this function before we take the derivative. So the PV stays the same, but now I'm going to do 1 plus r over 12 to the 12, all raised to the t. So I'm separating the 12 and the t, and I'm raising it this way. And again, the reason I want to do that is so I have an exponential function where the variable is by itself, which means this entire piece is the base. So when I take the derivative, the PV is a constant multiple, so that comes along for the ride. Then I get the original function back, right? 1 plus r over 12 to the 12 times t times the natural log of the base. So this is where I have to be extra careful because the base here is 1 plus r over 12 to the 12th. Okay, so this is the entire base if I want this in exponential function form. So it's a little goofy. It's a little hard to sort of algebraically manipulate, but maybe you figured some of those parts out. For part D, we're plugging in our values of P 1000, R is 0.025, and time equals 5 into our derivatives. So for our annual derivative, that's going to give us 1000 times 1 plus 0.025 to the 5th times the natural log of 1 plus 0.025. So again, we need to be really careful plugging everything into our calculator and use parentheses where appropriate. And we get 27.94. We'll talk about units in a minute. And for our monthly, when we plug everything into our derivative, we're going to have 1000 times 1 plus 0.025 divided by 12 raised to the 5 times 12 times natural log of 1 plus 0.025 divided by 12 to the 12th. Okay, this one is definitely more complicated to put into your calculator. You have to use a lot of parentheses and be really, really careful with all your powers. And when we plug everything in, we should get $28.30 when rounded to the nearest to 2 decimal places. So what are the units for these amounts and what do they tell us? So remember, we're going to do dependent units over independent units. So my dependent units were money, right? Future value was amount of money. And my independent units were in years. T was in years. So this tells me that when I compound annually, the rate at which my principal is growing is $27.94 per year at year 5. Similarly, if I compound monthly, then my account is growing at $28.30 per year in year 5. Okay, so again, these are rates. And this is one of the many, many ways that exponential derivatives help us sort of look at financials and things like that. So when people are on Wall Street and they're looking at stock markets, they will often look at the rate at which a stock is changing and sort of buy when rates hit a certain amount. And then when the rates slow down, that's like a key indicator that something is happening. So even though it's still increasing, the stock is still increasing, when the rates start to change, you can then make decisions about when to buy and sell. So this is helpful in business. We will look at some examples later in sciences, but hopefully this gives you sort of a peek into why taking derivatives of exponential functions is going to be really important for us in business for this particular. Okay, so we're going to stop here. That's our last example for the day. Again, just a reminder, you still have another mini quiz due on Sunday and the homework. So if you had any trouble with any of the algebra, just make sure you stop in to drop in help and ask about any of the pieces along the way. Otherwise, have a great rest of your day, and I'll see you guys on Tuesday.